started while the people are still coming in. I'm Judy Noodleman and a resident here. A few announcements. One, please silence your phones. And two, it looks like we may run out of handouts. There will be a sheet at the back. If you don't get a handout, if you'll put your name down and room number, it will get delivered to your mailbox. The other is the slides and the presentation will be on the portal as well. So just so you all know. So it's my pleasure to introduce Bill Schwartz this evening and to have known Bill since he arrived in Austin with the opening of Dell Medical School. Bill, a neurologist and scientist, served as professor and associate chair for research and education in neurology at Dell Med. Though retired from this position, Bill continues to teach students and develop our scientists and physicians of the future as a teacher in the biology department at UT Austin. Bill's own education included University of California, Irvine, and UC San Francisco, a research fellowship at National Institute of Mental Health, and then he completed his residency at University of California, San Francisco. Then Bill moved to the East Coast for appointments at Harvard and University of Massachusetts, and then in 2017 moved to Austin. Bill has had fellowships and awards worldwide and is a leader in the field of sleep. For over 4 decades, he has conducted NIH-funded research on biological clocks. The flyer about tonight's session made me smile, as it says he brings a lifetime of experience in your body's rhythm. While it may not be in your body specifically, he does bring a lifetime of experience in sleep and the rhythms of our bodies. Bill will return in February to continue his discussion on sleep. We hope you'll join us then, and please join me in welcoming Bill to the first of his 2 sessions at Westminster.
Thank you, Judy. I want to make sure I don't have feedback from this thing. Thanks very much for the invitation and the introduction. I thought what I'd do today, what I wanted to do on the second one was about sleep and aging, because all of us are getting older. But to prepare for that, I thought I'd give this session, you see there are 15 slides, so we'll be able to get through them without any difficulty. There'll be plenty of time for questions so that we have enough information to appreciate the issues about aging. And interrupt me at any time, scream out, not to scare me, but to stop me. All right.
Show your picture of the dog on the person. Here he is.
Yeah. It's not to say that you should be cohabiting with a dog to help your sleep, but everyone sleeps, right? So the big advantage of this is, of course, you're all experts in this. I mean, you know all about it on sleep, and the definition or the qualities of sleep you're familiar with. So, for example, one is the sleeper is relatively insensate, right? There's a higher threshold to external stimuli. You're not responding, relatively. Relatively immobile, normally, not moving. And of course, unaware, which is rapidly reversible. So the description of the behavior is that the sleeper is blind, deaf, paralyzed, and unconscious. Which seems like a pretty dangerous thing to do, as depicted in this detail of pain by Rousseau. And yet, it's persisted across the tree of life, which must mean it has adaptive significance. And so these are just examples. I mean, besides us, fruit flies sleep, roundworms, small jellyfish that's origin is almost 1 billion years ago. So this has been a feature of life, probably older than this as well. And we also know, you know, that sleep deprivation is known to be associated with all sorts of troubles in metabolism, physiology, immunology, behavior, vulnerability to illness and disease. Okay. So you know all that, and then I just wanted to show you this, that which I think this is a kind of an interesting, almost unbelievable graph. I'll use my pointer, which is this little red thing here. So in this experiment, subjects, normal volunteers, are given something called a psychomotor vigilance task. It's like a reaction time, sort of. How quick can you respond? You know, there might be a flash of light. How quick can you notice it? So it has to do with attention, you know, paying attention to what's going on. And on the axis here, whoa, yeah. This axis here is the speed of the reaction time. The faster the speed, the higher up on the graph. So we want people to be responding up here. And here's a baseline. There's a baseline how quick all of these individuals, it's about 4.0, whatever that number represents. So that's the baseline speed on this test when they've had 8 hours of sleep. So that's the baseline. Then what's happening going left to right is experimental days for a week. And these groups are differing in how much sleep they're allowed. So they're woken up. So the top one is allowed 9 hours opportunity. So actually an extra hour from what their baseline would be. And then going down, this group, the triangles, it's been shortened to 7 hours. So they're down by 1 hour, just 1 hour from the baseline. Here, it's down to 5 hours, so they're down 3 hours. Here, it's 3 hours, so they're down by 5. Okay. And then here it shows their speed on this reaction time test. So the people who are getting 9 hours of sleep, it's pretty stable. And you can see what happens, how this deteriorates every day. It deteriorates a little bit more. And it relates to how much sleep they're allowed. At this point, this is recovery here, recovery days. And you can see that the people who were sleeping the less actually do much better. But everybody who's had abridged sleep, all three of these groups, even after 3 days, don't get back to where they were. So you can't really make it up so easily, okay? It takes some time. So we can't really compromise on sleep in that way. All right. So if sleep is so important, why do we tend to sacrifice it as a dispensable state? Right? I mean, have you ever heard anybody say, I can't do that extra work because I have to go to sleep. No, it's the sleep. No, I'll stay up. I'll stay up all night. I'll stay up later. Why? I mean, since we know everything I've said, why? I don't know, but here's an idea. In the Christian Bible, the King James Version, you may be familiar with in Genesis, God caused a deep sleep to fall upon Adam. And it translates the same in Hebrew. And we say, I fell asleep. Oh, I fell asleep. I'm falling asleep. That means you're going down someplace. It's a state that's lower than being awake, right? I descend. I'm going down to sleep. When in fact, it isn't. And in many respects, if you're interested in your brain, it's really the time for the brain to be doing things. So this falling, and we say I fall asleep, is hypothesizing, puts us in a sort of state that, oh, well, it's a lower sort of state, approaching death almost. And, you know, in the European languages, I fell asleep, I entered sleep, I stayed asleep, and you see on your handout, so those of you who have it, for those who are not in the European, Western European, King James Bible, it doesn't go that way. In Farsi, Persian, I was taken away. Hindi, sleep came to me. In Igbo, don't ask me to say it, sleep carried me away, it took me up and away. So I think this sort of, unfortunately, has led all of us to sort of think of sleep as and it's only recently that people sort of realize that it's not. Sleep is actively generated. It's not a passive lapse of function. So although we won't get into detailed neurobiology, sleep doesn't come because wakefulness brain mechanisms go out. It's that wakefulness goes out and sleep mechanisms go up. Both of them have to. So it's active. It's not a default mechanism. And it's a composite physiological state. It's as complex as the state of wakefulness, really, what's going on during the time. Hormonal changes, immunologic changes, and so forth. So we'll talk about what might be the function of sleep then. So what's its function? So, you know, an old idea, and one that's sort of attractive, is that perhaps it's rest, saving energy. So we rest up, decrease metabolism. The brain doesn't actually stop firing during sleep. And this is an interesting paper that's very carefully done by a good group. In humans, if you calculate the total daily energy savings that would be associated with sleep by the change of metabolic rate, it's like 2 pieces of bread. So that cannot be. That cannot be. And I have to admit that, as quoted by these sleep researchers, there is no other area of neuroscience except perhaps consciousness that's so remarkably familiar and yet so difficult to define scientifically. So that's it, I'm done. No. So here's this may seem circular, but here's what I would say at the moment is the functions of sleep are surely multiple and are likely to be those functions that are best done when you're offline, not receiving everything from the outside world. I mean, like you can imagine with a computer, you would go offline, a computer to be doing things. You're blind, deaf, paralyzed, unconscious. it's dangerous, but you're offline, and certain things can be accomplished more efficiently or effectively, and there are probably many. One you can think of immediately is consolidation of memories. And this is a big topic in itself, but you can imagine if you were listening to me and also consolidating what you had for dinner at the same time, it might be confusing. So I think that's probably the way we have to think about it, is what are those functions? And it turns out that those functions can also occur when you're awake. There are examples of that, but not as efficient, not as efficiently. Okay. So just a couple of basic things, so we'll have some language. As I'm sure you know, in humans, sleep is recorded or analyzed by something called a polysomnogram, which is an electroencephalogram, an EEG, along with two other recording modes. So the EEG records brain waves, which are superficial. The recording is on the scalp. It's not in the head. People get EEGs if there's a question of epilepsy, for example. So there's the recording of brain waves. Then there's something called the electrooculogram, which records eye movements. And then an electromyogram, or EMG, which records muscle movement or muscle tone. And the combination of those has defined a number of sleep stages. So that's organized, not random. And here's a little picture of the kinds of brain waves that you might see on an EEG, simplified. So at the top would be the kind of pattern of someone who's awake, like you are now, where you get the very fast activity. It's a very low amplitude, like that, like you see there. And then, as you're becoming sleepier, here's awake and resting, which perhaps some of you are doing now, which is slower. The waves are slower in frequency. And here's what nobody is doing now, which is sleeping. And you can see the change, right? So the frequency of the wave, how the frequency of the waves is slower, right? So now, when you're awake, we can't even make out these waves. Now we're starting to see them here. These are called theta waves. They're related to the frequency. Sometimes called stage N2. And then one that we're going to talk more about is delta, named after these very slow waves, high amplitude, very slow waves that are weird. I mean, that's not the way your brain ordinarily would function. Okay? So that means that what it means physiologically is all these neurons, all these brain stems are all firing together and then not firing. Firing together and not firing. That's not the way it is when you're awake. That's called delta. It's also called deep sleep because it's the hardest one for people to be waking up from. And we'll hear more about that. And then, as you know, there's rapid eye movement sleep, REM sleep, which is sometimes called paradoxical sleep because, as you can see, the EEG looks like the person is awake. So sometimes it's called active sleep or paradoxical sleep. It was a big surprise, discovered in 1953. Many of us were, when I teach the students, they look at me, 1953. The other characteristics of REM sleep that are odd and peculiar is, by the name, consists of these very rapid horizontal eye movements and also complete paralysis, which is actually done by an active descending inhibition. Okay, so it's strange. It's a strange. I'll just put in parentheses, originally this was associated with dreaming, but dreaming can occur in other stages of sleep. It's not, it gets into more detail of the experiments, but it's not such a tight relationship. It may have to do more with the kind of character of the meditation. So those help define the stages. And I just will remember deep sleep, or this delta sleep. Now it's organized. This kind of chart is called a hypnogram. And what it shows is 8 hours of sleep. And on this vertical axis are the different stages. So MT is movement. So the person is moved or woke up. And then there's wakefulness, and then here's N1, which is this sort of restful stage, N2, N3 is this deep stage. Here's REM. And you can see there's a pattern here. So there's roughly sort of an oscillation here of every 90 minutes or so of going through N1 to N2 to N3 to REM, back to N1, N2, N3 to REM. So it goes repeating over the course of the night. Most of the deep sleep is accomplished in the first third or half of the night. And that it's almost done. And there's much more REM later in the night. And people may have had the experience that if you're up in the morning and you go pee and then you go back into bed and you fall asleep again, you're kind of likely to have dreams. And that's because there seems to be this bias sort of late like that. So that's the sort of basic landscape of our sleep, human sleep. Everything good? All right, so here's the important thing, the background thing that we'll need 2 weeks from now, or however it is, a month from now. Who could remember? The regulation, the physiological regulation of your sleep is an interaction of two processes. And I like to show this slide because you can immediately see 2 things going on here. So this is an old study, 1975. This is fatigue, self-related fatigue, from a Swedish experiment where they underwent 72 hours, 3 days of sleep deprivation, kept them up for 3 days. And then, at these intervals, they rated how sleepy they felt, how fatigued they were. And higher on this axis, on the left, is more fatigue, subjectively. And you can see that there are 2 things happening here very clearly, right? One is, over 3 days, they become increasingly fatigued, right? So the longer you stay up, the sleepier you get. Okay. But there's something else that's sort of superimposed on that, and that's this kind of jagged thing, which is every 24 hours. And so this is another sort of mechanism, and probably people have had it. If you've been up all night, suddenly you get a second wind in the morning. Even though you're still accumulating fatigue. So there are these 2 processes.
Yeah. In this study, was there 24 hours always occurring in the evening? Did they start the 24 hours in different, or was it always started in the morning?
The flattening, in other words, here, it's a good question. So this right here would have been the morning. and then sort of over the course of the day, over the course of much of the day, and then they start getting fatigued again. So they have that morning burst, sort of with the sun.
Okay, so everybody started their clock at the same time of the day.
Well, there's errors between. You're asking a very advanced question. So in the population, it all sort of merges.
But the notion is that it's during the daytime that they get that benefit or whatever.
Right.
Right.
The first part, there's a reprieve in the first part. And of course, this sort of gets more into clocks, and not everybody has the same clock, but they're all set by the morning sun and the morning light. And this is going to be a bunch of young people who are fit, and so probably the variation of the timing is less. But it's a good point. But these are the two processes that sort of regulate it, and I just, let me go and show you this, which is the only complicated slide, but it's really cool, so I insisted on showing it to you. So the one that relates to how sleepy you are is referred to as homeostatic regulation. And many may know what homeostasis is, which is in physiological systems that they try to maintain sort of a steady set point. And this regulation is the one that relates to how long you've been awake. How long have you been awake without sleep? And let me show you. The key thing here is, it turns out that this delta activity, the slow waves, the delta waves, the amount of that measured in a complicated way is proportional to how long you've been awake. So it's somehow aware. The generator of these slow waves are somehow aware of how long you've been awake. And so it's considered a marker of how much sleep you need. And here, in this experiment, this is a 36-hour sleep deprivation. Here's a night of sleep with this sort of, in this hypnogram sort of format shown here. And this is the activity, or the power, if you want, the amount of the slow waves over the course of the night. And you can see that most of it is in the beginning, and then it sort of drops down over the course. Then the person was sleep deprived for 36 hours, and then allowed to sleep. And what's been shown is that the recovery has a rebound, especially of this slow wave sleep. And when this is measured carefully, it actually accounts for what would have been lost. So something is keeping track of how much slow waves you're getting based on how long you've been awake. Maintaining homeostasis, whatever the slow waves are doing. And here's the opposite of that, which is also cool. Here's the same hypnogram of another group, of another patient, of another subject, again showing slow wave activity over the course of the night. And on this one, the person was given an opportunity to nap. Here it turns out about 6 p.m. And here you see they generate slow waves in this nap. And then afterwards they sleep, they go to sleep. And you'll see already here that the sleep post-nap slow waves are less than what the baseline was. Here in this little simple graph is sort of the amount, if you will, of slow wave activity. If we consider the baseline here of a night's sleep, call it 100% slow wave activity. Then here's the amount of slow wave activity in the nap. Here's in the post-nap, that is this night. Here's when you add them up and they match. So you deprive someone of the slow wave sleep, and when they get a chance to do it, it comes back stronger than before. And in experiments with animals and some complicated ones with humans, it matches pretty well. Something's keeping track. If you allow more sleep during the day, so there's less buildup, then that night there'll be less slow waves. So maybe we'll have time afterwards for questions or discussions about what are these slow waves doing for crying out loud. But this is the key evidence that there's some kind of physiological work that's being done while you sleep. It's not passive, it's not rest. There's some kind of work being done, and something is keeping track.
So what you're saying is more slow wave activity is beneficial to brain health, and not less slow wave activity is deleterious.
To repeat the question. So the question was, if you're talking about sleep health or brain health or general health, you should have more slow wave activity. And we'll get back to that because that's important. But in fact, for some functions, for example, like memory, and people who are having decreased memory, and we'll have this in a month, I have something on this. There are ways now to induce slow waves. This is early, also in Alzheimer's. And so the answer to your question is people are working with that idea. Yep. When you were in college? No. No, that's
a miracle. It's a
next
miracle.
time. There's one experiment I could show you. Maybe next time. I'll get the slide out about something like that. That's almost unbelievable. Of course, there's a lot of history with that too, right? Kekulé and the carbon ring had in a dream. The periodic table of elements came in a dream. Bohr and the structure of the atom, a dream.
Are you going to talk about insomnia?
Not today.
Oh, okay. Just that's what I'm curious about.
Yeah, because I wanted to get, we're almost done with these.
Right.
And this was sort of the setup about slow waves and all this sort of stuff, because then it'll relate to that. So the next one in a month.
But you're also assuming from all of this that most people go to sleep and get 7 to 8 hours of sleep. I can't remember ever doing that. What am I supposed to, as a child?
Why have these people heard this talk before? Hold on. Very, very perspicacious. Okay, I'll get there.
Okay.
So the other one, the 24-hour, and we heard about a clock, is right, a regulation that's based on your internal 24-hour clock. There is, as many of you may know, amazingly enough, there's an endogenous pacemaker, an endogenous oscillator. It's deep in the brain, in the part of the hypothalamus. It has a name, it's been identified, and it generates a 24-hour rhythm. The basis of it is molecular, but there are many other pieces to it. And that rhythm in that nucleus is synchronized to the day-night cycle, especially by light, and is necessary for the daily expression of behavioral rhythms, including the sleep-wake rhythm. So this is the way this kind of thing is shown. All these marks here are just activity. This is movement of an individual. He's active. This is the lights are out, lights are on, lights are out. And here you can see they're not moving, presumably sleeping, although this isn't a measurement of sleep. And across this axis is 48 hours. So you can see this clock-like regularity over 12 days from top to bottom. And then the trick is, how do we combine those two? So here's a little cartoon that I think is basically sort of useful or helpful. So we have these two regulatory mechanisms, the homeostatic, based on elapsed time awake, and the circadian, based on an internal timepiece. And here is, if we're going to look at this line here. It goes like this. And the higher it goes is wake, and the lower it goes is sleep. So here's the morning, and we're just watching. This would represent most all of us. So we gradually get more awake. We're up. Here's a post-lunch sort of dip in alertness. We're alert in the evening. And then we hopefully rapidly sort of fall asleep, not always, and then it starts over again here. And the idea is that this waveform, this wave, is actually the result of these two processes. One is homeostatic. So the homeostatic we might visualize as an increasing sleep load. That is, you're up all day and you're getting sleepier and sleepier. Something's building up, for example. Opposing that is this circadian signal, which is keeping you awake instead of falling asleep every 2 hours or so. And so this match is matched with an alerting signal that's counteracting this increasing sleep load. At some point here, bang, something happens. This alerting signal withdraws and allows the sleep system to generate the slow waves and sleep. So that's the idea between these two. And just in advance, when we talk about what might happen with insomnia or with changes in sleep and aging, already we can start thinking of kind of mechanisms involving these. You can see it won't be one. You can do it in a number of ways where you would have trouble. And so we'll go over that the next time. I just want to show you again to make the point, the final point, that the onset of sleep is not just a withdrawal of wake. It's a mutually inhibitory switch between wake and sleep. And not to memorize all these things, it won't be on the test, but there's a set of wake active centers and a different set of sleep active centers, and they're opposing each other. So they're inhibiting the other, and then they withdraw and they inhibit. So again, sleep and the generation of sleep and falling asleep is an active thing. You're being carried away with sleep. So this raises the question of how do I know if I'm getting enough sleep, right? And we heard about things like this that we're told about how many hours should you sleep. Should. We're never supposed to say to our kids, you should, right? You already know there's a problem. Anyway, this is all over the place. And for us, all of us, you know, they say we need 7 to 8 hours of sleep. And that's the need.
Hey,
This makes no sense, right? Because we just got through saying that, you know, there's physiological work being done during sleep, right? So and even though we don't know what it is, say it's memory or something, presumably that work could be done if you slept shallowly for a long time or deeply for a short time. And there are people, of course, who sleep 6 hours, right? And they're okay. There are other people who sleep 8 hours, they're okay, okay? So the reason don't tell anybody this, I won't get a job anywhere. The reason this is because it's easy to measure duration. It's hard to measure quality. It was hard to measure slow waves. Now we can do it. So now it's done sort of by fancy machinery. So now we can get a much better idea of sort of what the work might be or what the benefit might be. I will say that no matter how deeply you sleep, there does appear to be a lower limit, which is below 5 hours, you can't make it up by being, you know, deeply asleep. So there's a limit. But obviously, if somebody ordinarily sleeps 8 hours and is now getting 6 hours, that may be a problem. If somebody ordinarily gets 6 hours and is okay, that's not a problem, right? And so what we really need is, in addition to duration, it's going to depend on all these other things, right? Which people generally measure duration. So it's going to depend on how fragmented is your sleep, the timing, that is the timing of it, early or late in relationship to the outside world, the intensity, the depth, the rhythmicity, how clean is your wakefulness and sleeping is your sleepiness, and then every night how regular is it. And so again, I'm sorry that the answer is, I think this at the moment, that if you ask, am I getting enough sleep, you're presumably getting enough sleep if you're not falling asleep when you don't want to. Sorry. Yeah. I mean, we have no biomarker, really, right? So if you're not sleeping, you're probably okay. Seems circular, but the field is advancing. Here for your handouts, you know, this is something that's everywhere about the basics of sleep hygiene that I think you know. The idea is not to use the bed generally for other things besides, if you're having trouble, not to use the bed for things other than sleeping. The regularity of the sleep schedule is important, that's the clock. You don't want to get yourself into a state. So often people who have insomnia then get scared or fearful of sleep. I'm not getting enough, and then this will obviously keep you up. Easier said than done. Of course, caffeine, alcohol near bedtime, because it sort of wears off and there's a rebound. You may wake up in the middle of the night. Nicotine, darkened room, obviously. Everyone on TikTok knows about light-emitting screens before bedtime. And the idea there is it's fooling your internal clock that it's still light out. I like this one. Go ahead and resolve concerns or worries before bedtime. Go ahead and do that. Good, it's a good idea. Exercise is good, but not too close to bed. That's true. And then the daytime naps are beautiful, but not like at 6 p.m. Yeah. So I think we now have enough to sort of look at what's happening with aging a month from now. Yeah, that's right. Oh, you'll lead to, yeah.
So when the legislature passes a rule that says that we get to vote on whether we're staying on daylight saving time or not, do we vote for it or we vote against it?
Against it.
Okay.
And there's science, there's a rationale behind that, yeah. And it's especially important for people who live on the western edges of the time zone. What do you think about that?
So we're for
Standard time.
leaving it the way it is,
Yeah.
Standard. The best would be standard the whole time,
but not switching back and forth.
not switching either.
Okay. Got it.
Your chart here that showed the deep sleep, REM, awake and all that, is there a preferred balance? I mean, should you have like 30% deep sleep and 20% something, or is it just fluid for everybody, or is there an optimal amount?
Yeah, so, I think it varies. I will say that the people, and this has been studied, the people who are naturally short sleepers, like 6 hours, when you look at their graph like that, they've sacrificed REM, they've sacrificed some of the N1, N2, and they've preserved the delta. So so the deep sleepers are having a better mixture of slow wave sleep, or delta sleep. And if anything, they're getting rid of the REM.
Well, in the graph that you showed, where you showed the two opposing processes, and you stated that something was withdrawn from the act of stimulation. Isn't that obviously daylight?
Yes, in the sense that the light interval is setting the clock in a certain way.
Yeah,
So
it's
so
tied to that light interval, right?
that's the synchronizing
Okay.
thing. Although, as was brought up here before, people's clocks synchronize with somewhat different, yeah.
They're not all accurate.
They're not all bad. We don't all go at the same time.
And in the first slide you showed about the sleep, I was surprised to see how many times, which I presume was an ordinary example, people woke up during the night. They get all the way to waking in the slide you showed.
Yeah, some of them are, it would be an EEG sort of wakefulness in that sense. So it might be awake and rested. The sleeper might not say they're awake. So it's not quite the same thing as they get up to go to the bathroom.
I was thinking it made me feel better about all the times I wake up every night. I did that now.
Yeah, I'll show you in a month what ours looks like.
Well, as you may have guessed, I do suffer from insomnia, as did my mother and my daughter. I wonder if it's somewhat genetic. But what I've found is, and I don't know how I discovered this, in the middle of the day, sometime, like at 1 in the afternoon or something, I can go into what someone has told me is an alpha state. And I don't know how I learned to do it, nobody ever taught me, but it's like plugging into the wall to be recharged.
And are you napping or not?
I'm napping, but I'm not asleep, I'm totally
You're
awake.
just in a state.
If somebody walks in and asks me a question, I can answer it, but I don't move. I just stay there, and then when I'm through with that, which is usually between 15 and 35 minutes, I'm totally recharged after that night of insomnia.
And is there a history of like, things like sleepwalking or sleep
No,
talking in the
no.
family?
No,
When you're plugged in, do you glow in the dark or anything?
maybe, but it's fascinating.
Yeah.
So you were talking about all that, and I thought, well, alpha, that relates, whatever.
Yeah.
Somebody said, well, this is alpha state, and you can learn how to do that. I mean, people can teach you how to go into that state.
Wow.
It's kind of a maybe meditative state, but nobody ever taught me.
You can do a workshop
I
and teach us
could.
how to do it.
It's fabulous, it's really.
Why do we get sleepy after eating a big meal?
Part of it is clock driven, but I think we don't know, really. I mean, there's a metabolic load, but that's a good question.
The energy goes down.
Yeah, I don't know about that. Yeah, I'm not sure.
Yeah. I have a question. I dream a lot, and I'm sure I'm very active also physically when I dream. What is the relationship between that and sleep? Chart.
You mean you're moving while you dream?
Yes.
And how long has that been going on? Or is that all, you've always done
I've always done
that?
that.
Always done that. So, and have you injured yourself or no?
No.
Or your wife?
I can be dreaming that I'm running or bicycling, and all of a sudden I wake up and I have been actually moving my legs.
And do you have you ever had dreams where you know you're in a dream?
Well, I have wild dreams.
Wild dreams.
Yes. And
Well, this, for some of these active dreams, which might preferentially be in REM sleep, the circuitry that paralyzes you depends on a lot of, it's not just one set. It's a lot of connections, and presumably for you, if that's always been the case for you, that neurobiology, those connections are somewhat weak. And so you're not completely paralyzed during those dreams, would be one idea.
I was wondering, what happens when you're tired, you go to sleep for 1 hour, then you can't sleep for 4 or 5 hours, and then you can sleep in the morning.
So, well, we'll touch on that actually the next. But for example, if you imagine this sleep system and this weight system, and ordinarily they're, when we're babies, bang, you're out. Up, out, like this. As we get older, lose some gray matter, as we all do, maybe this wobbles a bit. And so it's not clearly sort of in the on or off position. That would be one sort of idea. Now, how we can fix that, well, the sedative hypnotics that tend to do it, but they have side
in your next presentation, are you going to discuss certain disorders like restless leg syndrome or REM sleep behavior disorders?
Well, it depends if they give me more time. I start next week, I give a semester-long class to undergrads on sleep and sleep disorders. Yeah.
Okay.
So even though you guys are clearly brilliant, in 2 hours, but maybe by popular demand.
Okay. I have a hypothetical question. What if a world leader was up at 2 or 3 in the morning posting online, intending to fall asleep during the day during his important business meetings? Would that be of concern to the population?
Which population are we talking about?
It's hypothetical. It's hypothetical.
Isn't that the truth?
So I'm not sure that this applies, but why is it that when some of us get up in the morning, we do our most productive work in the first few hours before anything else happens?
So some are like that, and some are the opposite. Right? So these are, oops, can't lose this. These are larks and owls, right? And there's a range in the population. We understand quite a bit now about how that might happen related to the function of this internal clock. And for me, writing, I can only do it in the morning. If I do it in the evening, I just go in circles. I mean, it builds momentum, so I may try it, but then I know in the morning it'll just sort of go. For others, it's the opposite. So our daughter is a night owl, and she would be doing composing and everything, at 3 in the morning. There are a number of these people, these so-called delayed people, and the problem for them is there's nothing wrong with them, it's just that they're out of kilter with society. So, being a sleep doctor, I gave her a prescription of what, not a drug, but a program of what to do, so we could move her forward, and it succeeded, and she said, like Benny, I don't like it. I don't like it, yeah. So like some people have a susceptibility to hypertension or ulcers or whatever, this early bird night owl thing, it really relates to features of our clock.
Are you going to talk about drugs?
I wasn't going to.
Next time.
Well, you mean as a medical, I could a little bit.
Sleep drugs, yeah.
Sleep drugs, yeah.
Ambient type things.
Yeah.
Melatonin.
Oh, yeah. All right, I'll add that. Okay.
Well, if we got any more questions, I think we'll say thank you very much, and everybody have a good night's sleep.
Thanks for your earlier questions.